bit for us. So electrons are the negatively charged subatomic particle in atoms. Okay? In an atom, if we have 7 protons, we're going to have 7 electrons. It's going to be neutral. However, those electrons don't just sit inside the nucleus. They actually sit in an electron cloud which orbits the nucleus, and they have set energy states, which we know as shells. Okay? So those shells are certain distances away from the nucleus, and they can only hold a certain number of electrons. Who knows what each of those shells can hold, and who knows the name of that shell?
And the reasoning why.
Okay. Who wants to go first? Georgia.
Isn't there 2 in the first shell?
Okay, so we've got 2. That's on record. We got 2.
And then isn't there 8?
Then 8.
18? Is it 18?
8 or 18, I'll put down. And then lots. How about that? Okay? Now, some of you may have been told like 2, 8, 8, and then some more. Some of you may have been taught 2, 8, 8, or maybe 18, and then some more. But you want to basically now, at this stage, know why that's the case. But basically, we have shells. Okay? And the shells have names. M, K, L. I think I've got that wrong, actually. L, K, M, N makes a little bit more sense. No, it doesn't. Wouldn't this make sense?
There you go.
That would make sense. And in fact, that's what it is. Okay? Now, this shell can hold 2. This shell can hold 8. This shell can hold 18. And this shell can hold 32, I believe. Let me just do some maths. 14 at 32. Okay? But if we write the electron configuration out of, say, potassium, what does that equal? The electron configuration of potassium. It has 17 electrons, if that helps. Okay, so we've got 2 in the first shell. How many in the next? 8.
Wait, how many electrons?
17 total. No, 19 total. 19 total. 9 in the next. But we're saying it could be 8 or 18. So how do we know which one it is?
I say it's 18.
Okay, you say it's 18? You say it's 18?
You know, 18 doesn't make
This
sense.
doesn't.
You know what?
Again, it's undetermined whether which one it is.
It's not undetermined. It's undetermined for you at this stage. Okay? It is actually 8.
Then why was I taught 18? I'm sorry.
I'll explain. Okay, which means how many do we have left? If we've got 19 total? We've got 1. So that would be the electron configuration for potassium. 2.8.8.1. Okay? Some of you are like, why did we get taught 18? Some of you might not have been taught that. Yep.
Would it?
For our purposes, we're going to mainly concentrate on shells. But it's actually slightly more complicated than that. In fact, it's got orbits as well as shells. And let me explain. So the best way... Okay, so I'm going to attempt to show you actually how those electrons are organised around an atom. So if we think about maybe... I'll try and do this in 3D and then I'm going to draw a different picture. Let's say this is my stage and we're all come to watch my good friend Beyonce perform. Okay? Here she is. I think I've nailed it. Okay? Now, if you were to sit and watch this Beyonce concert, where would you sit?
There's no seats.
There are no seats. Where would you put the seats to watch her?
In front of the stage.
Around her. So we're going to put a seat, we're thinking 3D, but we're going to put a seat here and here. And these are going to actually start representing our shells and orbits. Okay? So this would be the first shell. Okay? This would be our K shell. And you notice it's got these two seats that are right around her in that orientation. Okay? We're going to call that orientation S. So sitting around her would be orientation S. Okay? And it can hold 2. The next shell is L. So these are slightly cheaper seats. They're a bit further away from Beyonce, and there's in fact 2 orientations that you can watch her in. So again, we have these 2 in this orientation, but sitting slightly further away, not as good, but we're still watching her on that orientation. The next orientation is going to be something different, okay? And in fact, it's going to go around her instead of this way around her. It's going to go this way around her. Okay, does that make sense? Okay, so the seats are going to go like this. Actually, I might do them in a different colour so we can track the shells. Okay, we'll do red. Okay. And so we can actually go right round her in this orientation. And I'm going to do these in circles. So we get sort of this shape around her. Make sense? No? Have I lost people?
And then you got the diagonal one.
Yeah. So that orientation with that width away from her, we're going to call P. Okay? So in that L shell, that set distance away, we have the people sitting in that original orientation, but then we've got another 6 people that can be seated around her in that orientation. Okay? And then we can go to the next shell, which we're going to call M. And again, we can sit 2 people in that original orientation. We can sit another 6 people in this orientation, but then we can fit another 10 people, no one wants these seats, in, say, this orientation. Okay? And that can hold 10, and we call that orientation D. Okay? So now we've got, oops, I don't know why I did it in blue, sort of ruined my thing, but that's okay. 2, 6, and 10. So if we count them up, let's have a look. We've got 2 in K. We've got 8 in L. Oops, yep. And we've got 18 in M, the third shell. Okay? Then we've got N, which has the 2, the 6, the 10, and then it's got another orientation that can fit 14 in it, which we call SPDE, I believe, but I will check these for you. Okay, so then that one can hold how many? 32. Okay, and it keeps going. Okay, but we don't just fill from 2, so we don't just go from this 2 to this 2 to this 6 to this 2 to this 6 to this 10 to this 2 to this 6 to this 10 to this 14. Okay? Because chemistry is weird. In actual fact, we go from this 2 to this 2. Then we go from this 2 to this 6. Then we go from that 6 to this 2. then we go from that 2 to this 6, then we go to this 2.
Why though?
Because basically, if this was watching Beyonce, people would rather sit a little further away but be seated around her than being suspended around her.
I don't know about that.
Okay, in terms of energy. Okay. Now, once we fill up those 2, we then go back and start filling up these 10. Okay. So this is the way chemistry works, and these are called orbits. So rather than orientations, they're called orbits. So in the first shell, we have 1 orbit. In the second shell, we have 2 orbits. In the third shell, we have 3 orbits. In the fourth shell, we have 4 orbits, 5th orbit, 6 orbits, 7 orbits, 8 orbits, etc. So in this example, we've got titanium. Titanium has 22 electrons, and we're going to start filling our shells, filling in the correct orbit order. Okay, how many in the first shell, S orbit?
2.
Okay, so now we're down to 20. How many in this S?
6.
In the P?
6.
6.
I don't know why I put lines through them. That annoys me. 2, 6. So now we take 8 off. 20 minus 8 is 12.
One more than
And then, how many in this S, Andrew?
that would be
2. This P?
6.
This D?
Wait.
Wait.
That would be 2.
Okay, so
The D has 2.
we would normally, so we'll take another 8 off.
The D does
Take
have
a
2.
chip pill. Just
Remember,
yes.
all of you guys are on the recording, which your parents I encourage to watch.
Okay. Yes. Thank you. It's cool.
Okay, so what's 12 minus 8?
4.
Okay, so now we go down to this S because we know that's the filling order, and we put a 2 here. Okay, so now we're down to 2, and we go back up, and now put another 2 in that D. So that D would be able to hold 10. Okay, so eventually, everything sort of next to what we're looking at now is going to be filling up this S, so after calcium, this S, and then filling up all of the D. Okay, so we're now down to 0. So we add them up. S equals 2, this one equals 8, this one equals 10, and this one equals 2. So we would write 2.8.10.2. Okay? Now, our next lesson, and something we're going to be really focusing on, is how does this electron configuration determine an atom's position on the periodic table, and then more importantly, what's so special about this last one? Okay, that's for tomorrow's lesson.